Hello and welcome. Today we're going to be learning about some of the math behind World War II. More specifically, the math involved in what we call projectiles. So a projectile is any object that is launched with a certain speed and with a certain angle. So here we have a footballer who is throwing a football. He's going to have obviously some amount of range, and that football is going to follow what we call a parabolic arc. And we've already learned a lot about parabolas. So what we're going to do is we're going to take our understanding of parabolas and we're going to extend this to include real life situations. And the real life situation, of course, is going to be about World War II, as we've been learning about. So in your social studies class, you've already seen some examples of the technology used during World War II. We're going to pick out some of those pieces of technology that involved projectiles. And I say technology because this is going to have a pretty big range. So we'll have weapons such as missiles. So missiles have a long range and a very high initial speed, as you can probably imagine. We also have what are called mortars. Mortars have pretty high speed as well. They're shorter range, and as you can see, they have a higher angle of trajectory, so they're going to go a lot higher than a missile would, which means they're going to fall a lot shorter, and they'll serve a specific purpose, which you will be going into investigating further if you choose to make an equation for a mortar. There's also grenades. Grenades are going to be similar to a football, where they're limited to the strength of the person throwing them, much shorter range, much lower velocity. We also have paratroopers. A paratrooper is someone who parachutes out of a plane to land in a certain area. And so this is a little bit of a different projectile. This is a little more difficult. If you would like a challenge, this is going to involve the arc that is followed by parachutists as they fall through the sky. However, to help you understand this, I'm going to be picking an even older piece of technology, the cannonball, and I'll go a little bit into how to make an equation for the trajectory of a cannonball. Now, before I get too far into the finding the equation for the parabola, we need to understand a couple more things about the trajectory of a projectile. So here we have this image, this GIF actually, that's playing over and over again. It's showing what's a little animated cannon firing this large red cannonball. And you can see it's firing directly horizontally. There's no angle here, or you can see the angle is 0. And so what happens here is you can see this larger arrow, which is horizontal, is modeling the velocity with which the cannonball leaves the cannon. And then this vertical arrow that you can see growing as it moves is representing the force of gravity. So when the cannonball leaves the cannon, it's more affected by its horizontal motion, and as it continues to travel along here, gravity is going to pull it more and more down, which is why we get this arc. So it seems, so if you look here, the dots are almost horizontal from each other, and then as time moves on, they're going to slope downwards, and as we know, parabolas will eventually look as though they are almost completely vertical. So as I mentioned earlier, the parabolic arc formed by a projectile is going to depend entirely on its angle and initial speed. So we can think of angle as how high or low we raise our cannon or missile launcher or mortar, depending on what technology you choose, and the initial speed with which the projectile leaves the cannon or launcher or mortar. So this is a pretty cool application that I found that will be available on the class website, where you can kind of start to see the relationship between the angle and its parabolic arc and the speed in its parabolic arc. So here let's start by launching our cannonball at 45 degrees with an initial speed of 18 meters per second. So this simulates the parabolic arc that this cannon would potentially follow. And what we're going to do next is we're going to see what happens when we change the angle, and then we'll see what happens when we change the speed. So let's raise the angle up to 55 degrees. Let's launch this cannonball a little bit higher. So you can probably guess that what's going to happen is it's going to reach a higher level of elevation, but it's going to have a shorter range. So we can kind of think of this top arc as the path more likely followed by a mortar, and then this bottom arc would be what would be more likely a missile. Not as large of an elevation, but a lot further. Okay, and then let's, just for fun, let's bring it down to 35. And remember, we're keeping the initial speed the same. So the cannonball is leaving at the same speed, but it's going higher or lower depending on the angle. So not surprisingly, we have a shorter parabola. But we see it doesn't go as far. So we'll get to investigate why that is, how that happened. You might have thought it would have gone a little further, but really we would have had to raise the speed a little bit for that to be the case. So let's see what happens when we do change that speed. So let's bring it back up to 45 degrees for the angle. Okay, I think you guys can all figure out what's going to happen, but let's see what happens if I now increase our speed to 30 meters per second. It's going to go a lot further. A little bit more goes a long way. And then let's see. It's kind of fun to watch it. What happens when we bring it down to 5 and the cannonball just doesn't even make it anywhere. So speed and angle are going to have a huge impact on the parabola. So now that we have got a little more insight on how parabolas are formed, let's pick out a specific cannon. Cannons have been around for a long time. And as you can imagine, there's been a lot of different renditions, a lot of modifications. So if I'm going to investigate the parabolic arc that a cannonball follows, I'm going to need to pick a very specific cannon. So here we have what's called a Napoleon 12-pound light cannon. Or sorry, a light field gun. They call them guns, but we think of them as cannons. So what I did is I looked at a little research, and there's this website called civilwarwiki.net, where some people have been nice enough to lay down some of the statistics behind some of the war technology used during the Civil War. Now, of course, we're interested in World War II, but again, I wanted to give you guys a little example, so I picked a weapon from an earlier war, much earlier. Okay, so you can see we've got a lot of things here: type, rarity, years of manufacture. We're not interested in that. We're interested in two pieces of information: the muzzle velocity, which you can see there. So this is going to launch at 1,485 feet per second. So this kind of cannonball is going to cover almost 1,500 feet in 1 second. That's pretty dang fast. And this has an effective range at 5 degrees, so it's kind of easy to miss, but that 5 degrees is actually going to be our angle of elevation. So that's a really shallow angle. So these cannonballs, they didn't launch cannonballs straight into the air, and in fact they more horizontal than anything else. Okay, and then launching this at 1,485 feet per second at 5 degrees is going to give them a range of up to 1,619 yards. So this will launch cannonballs 1,619 yards. Now that I picked out my piece of technology, that Napoleon 12-pounder cannon, I'm going to get to start developing a strategy for finding the quadratic equation that the cannonball is going to follow, that parabolic arc that we've been talking about. So I need to record some of the information I've found. So after conducting my research, I found that the muzzle velocity, or the initial velocity, of that cannon was 1,500 feet per second. So this little symbol here, we call that knot. V naught would represent the initial velocity, so the amount of momentum it had directly after it was launched. We also need to include the angle at which it was launched, and that we're going to call that theta. That was 5 degrees. And then we're also going to need to keep track, or we're also going to need to know the range. So the range was given to us in about 1,600 yards, and we don't want to be using feet and yards, so we're going to convert our range from 1,600 yards to 4,800 feet. Okay. So now it's going to be helpful if we draw a little bit of a picture for ourselves. So when we're developing these functions, we actually get a lot of freedom of choice. So one of the first choices I'm going to make is I'm going to consider my cannon to be at the origin of the x and y plane. So if this is my y-axis and this is my x-axis, we're going to assume my cannon is right here at the origin. And if I consider the possible arc this cannonball is going to make, so it's going to be kind of a long, shallow arc based on just what I know about cannons and how they behave. And the first thing we're going to do is well, first of all, let's write down, I've got our angle of 5 degrees there. And we know that the range is 4,800. That means that if it starts here, it's going to end all the way over at 4,800 in the x direction. And of course, if we say that the ground is at 0 on the y-axis, then this is going to have a value of 0 for y. So as we learned previously, to define a parabola or a quadratic equation of this type, all we need is that one point and the vertex. Remember, the vertex is the maximum or minimum, in this case, the maximum point. And we also know that parabolas are symmetrical, so if I think of this as the vertex here, then that's going to be directly halfway between the cannon and where the cannonball lands. So right here it's going to be exactly half, or 2,400 of 4,800. And this point right here is going to have a value of 0, but we don't want this point, we want the vertex. The vertex is going to have that same x value, 2,400, but we're not really sure what the y value is going to be. We weren't given that information, so we're going to have to use some strategies to figure it out. So before we start figuring that out, we're going to need to get a closer look at what I was talking about in the very first animation I showed you. So we had this idea that if this cannonball has some angled trajectory, so this is what we call a vector. Vectors represent velocity. This is a velocity. This is going to represent the velocity of 1,500 feet per second. And any angled velocity is going to have some momentum or speed in moving in the x direction, or the horizontal direction, and some speed in the y direction. So if something is moving at an angle, then it's covering, you can think of it as it's covering ground, but it's also increasing in height. So we can actually think of this vector as being composed of two other vectors. A vector in the horizontal direction, which we're going to call Vx, and a vector in the vertical direction, which we're going to call Vy. So again, this 1,500 feet per second at 5 degrees is going to be covering some horizontal movement, but it's also going to have some vertical movement, and of course it's then going to fall back down to the force of gravity. So if I take this vector here and I just move it over there, which I'm allowed to do, I can see here that I created for myself a right triangle, which means we're going to get to use everybody's favorite area of math, trigonometry, to determine the value of Vx and Vy. So starting with Vy, we find that, I apologize, let's back up here for a second. Using what I know about trigonometry, that old phrase SOHCAHTOA, so being for sine, sine is opposite over hypotenuse. So the sine of 5 degrees is going to be equivalent to the opposite Vy divided by the hypotenuse, 1,500. Oops, sorry, 1,500. And if I solve for Vy, I'm going to find that the velocity in the y direction is actually equivalent to 1,500 times the sine of 5 degrees, which, using a calculator, we find out comes to 130.734. And we'll talk about what that means in a moment, but let's go back and let's now look at the cosine. Cosine because we now want the adjacent angle, or adjacent side, over the hypotenuse. So cosine of 5 degrees is going to be equivalent to our velocity vector in the x direction divided by our initial velocity of 1500. So again, that's going to give us that the velocity in the x direction is 1500 times the cosine of 5 degrees, which is going to be equivalent to 1,494.292. So just using the calculator again. Okay, so now we have the velocity in the x direction. So notice that the movement in the x direction is much larger than the movement in the y direction, which makes sense if we go back to our picture here. We cover a lot more ground horizontally than we do vertically. Because of how a cannonball works is that we don't want it to go too high up in the air. We want it to cover more ground vertically. So it's only moving vertically at 130 feet per second, but it's moving horizontally at 1,400 feet per second. If you chose to examine the mortar again goes a lot higher. It doesn't go as far. So that in that case, we might actually find the opposite is true. So now that we have this information, we're going to be able to use this to figure out what that y value is. So again, our goal is to determine the y value at this point. So we already know that the x value is 2,400. And we want to fill in this blank here. If we can fill in that blank, then we can use this point and this vertex to start developing our equation. Our function. To approach this, what we're actually going to do is we're going to develop two different equations. This might seem kind of moving in the opposite, like we're moving in the wrong direction here, but we're actually going to create two equations that are going to represent the position of the cannonball in terms of its horizontal motion and its vertical motion. So the horizontal motion is really straightforward. We're going to call this x naught. X naught is going to represent the x value of the cannonball. So let's say x naught was 5. That means that we're talking about 5 feet away from the cannon. Not 5 feet on this path, mind you, but 5 feet over the ground, or as the bird flies, if you could use that expression. So x naught is really straightforward. It's just going to be the velocity that we just found, that 1,494.292. It's going to move this many feet per second. So if I think of, let's say, t, if we let t represent time in seconds, then I could create an equation where x naught, its position in the horizontal direction, is how fast it's moving multiplied by time, because of course distance is equivalent to speed or rate times time. So we're not interested in just any old position, however. We're interested in where the x value is, or where we want to know the y value, but we want to know what the x value is going to be right here. So I already know its position is going to be 2,400. What I'm actually going to do is I'm going to figure out how long it's going to take the cannonball to get to this point. It's going to be at that point exactly when it's moved 2,400 feet in the x direction. So I'm going to say, well, I want to know what's going on exactly when x naught is equal to 2,400. And I'm going to find out how long it's going to take to get there by solving for t. So once I've divided both sides by 1,494, I find that t is equivalent to 1.6, roughly. I did a little bit of rounding. So what that means is that exactly 1.6 seconds, the cannonball will be at that vertex. It'll have made it exactly 2,400 feet over the ground. Now the x direction is simple because the only thing determining the position of the cannonball horizontally is how quickly it was shot out of the cannon. However, its vertical position is actually based on two different things. It's based on the velocity of the cannon, but as you can see, it comes back down. That's due to gravity. So it's also going to be affected by gravity as it's moving. So I'll have to explain to you guys a little bit more in depth later on why this is, but the force of gravity is actually going to be considered negative 16 t. Remember, t is time squared. So the force of gravity is actually negative 16 feet per second squared. That's the acceleration that you're pulled down. And again, we'll go, I don't have enough time in this video to really get into that, but we're just going to leave that as it is. And we're going to add on its momentum from the cannon, and that was, again, 130 feet, roughly 130 feet per second. Okay? So again, this is negative because gravity is pulling it down, so gravity's going to pull it down into the negative direction. Obviously, it's never actually going to go negative because that would be going into the ground, but it'll hit zero at one point. And then this is its momentum being pulled up. So you can think of these as two opposite forces. We have the force pulling the cannonball directly up. We have the force pulling the cannonball directly down. And these are both going to give us the position of the cannonball in the up or down direction. So again, it's not going to tell us about where the cannonball is on this parallel path because that's our end goal. What this is going to tell us is how high up or down on the y-axis it actually gets. And its largest y value is actually going to be right at the top of that vertex. So but let's go back. We found that after 1.6 seconds, that's when the cannonball is going to be at that point. So now all we need to do is plug 1.6 into our equation here. Oh, well, that's not. Let's back up here. Actually, plug 1.6 in there. Okay, and after some algebra, you will find that this is exactly 168.6995. And that is in feet. So I know I skipped a couple steps there, and we can, if you would like, I can go over that a little bit more in depth in class. But essentially what we have here is that we have found our y value. After 1.6 seconds, this cannonball will be exactly 168 feet in the air. And again, 1.6 seconds is also happens to be when it is at that vertex. So we have now found our y value. It's 168.6995. So when this cannonball is at its peak, it has gone exactly half the distance, and it is at 168.6995 feet in the air. So here we have what's called Desmos. You can find it at desmos.com. This is a free graphing tool that we'll be using throughout the year, or have used a little bit already. But just to recap, once I've clicked in this field here, so normally that toolbox isn't there, but once I click in this field, it pops up, and I can start typing in that equation. So the equation I just derived, it starts out with a leading negative coefficient of negative 0.000293. And then to make an x squared, I type x, and then this little a squared button there. And then I'm going to add on the coefficient of 0.14064 with an x following it, and that's going to be my equation right there. So this looks an awful lot to me like the arc of a cannon, or the arc a cannonball will follow, starting at our initial position of 0, 0, that's where we placed our cannon, and ending over here at 4,800 feet. So that's where our cannonball landed. But we're not done yet, because after you've created your parabola and your equation, I'm going to be asking you guys to develop additional ideas. So obviously, I'm hoping that we all understand that the world is not this simple. There are lots of other factors at play here, and I want you guys to make a list and even start to explore some of those additional ideas. So, for example, I didn't take into account that the cannon had a certain height, so how would that have changed my equation? Can I just plug that in now, or is that something I had to consider at the beginning? We talked a little bit about the mass of the cannonball. So thinking that a larger cannonball would require a greater amount of force. So maybe I could start to think about how much gunpowder I would have needed to launch this cannonball. I could think of different angles of trajectory. So this is the furthest a cannonball can go, but sometimes you might want to fire the cannonball a little closer and how the arc would change with that. Another big thing we didn't even consider that's a lot more complicated is air resistance. As objects move through the air actually pushes back on them, and they'll lose momentum over time. So the cannonball would have actually fallen much shorter than that had we considered the air resistance. So that would have changed our function as well. So essentially, this is an adequate function for a model, and I can answer questions about how far the cannonball will be at a certain amount of time. But if I wanted to get really into it and I wanted to get really realistic about this, I would have to think about some of those other elements. I also would like you guys to consider what it would be like to operate a cannon or a missile or a mortar or what it means to drop a paratrooper and the kind of decisions that someone would need to make. So, for example, if I'm running this cannon, I need to really think about the angle at which I launch it, and I need to think about how much gunpowder I'm putting into it, and I need to think about how swiftly the wind is blowing, or if that's even a factor, or how I can overcome that. And so those are some of the ideas that I want you guys to be coming up with to answer our essential question of how war has changed throughout time. Now that you have seen one example of a quadratic parabolic function, now that you have seen one example of how a quadratic function can model the trajectory of a projectile, I'm going to ask that you and your partner make a decision about what kind of technology from World War II that you guys would like to investigate, whether that would be the missile, mortar, a grenade, or the path of a paratrooper. Or if you find some other piece of technology that follows an arc from World War II, if it's approved by me, you're welcome to research that. So you're going to start out by just kind of doing general research and investigations into technology, and start to think about some of those variables that I talked about, the air resistance, the height of launch, and those kinds of things. Each technology is going to present a different level of difficulty, so think about that as you move forward and as you conduct your research. If you need additional help, please visit khanacademy.org. They are a great resource for additional information about anything, but specifically about parabolas and quadratic equations. As I mentioned, I use Desmos.com, and we will be using Desmos.com to graph our information. Once you and your partner have conducted your research, found your equation, and made your observations, you will be compiling all this information into a presentation. And how you guys present the information is entirely up to you, as long as it is appropriate. If you would like to use the same technology I used to make this video, you may. It's called Screencastify, and it's actually an application that you download. So it does have its own site, but you can just go into Google and type in the word Screencastify, and you'll be directed directly to that. Thank you for watching, and I hope you guys enjoyed this project.